So you might notice I have taken almost all the keywords from John in my title. There is one missing, it's convection, which I have replaced by libration. So I will not be talking about convection at all, almost. And the second point is that I will be talking about turbulence, but the turbulence we have seen up to now mostly looks like that. So very elongated structure along the axis of rotation. And actually there is a second completely different type of turbulence in rapidly rotating system, which more looks like that, and which is made only by weakly nonlinearly interacting waves. Okay, so as an introduction, let's start with something that is most easily seen, the surface of the ocean. So in this picture, you also can notice two different types of turbulence. The one that we are used to is here, with big vortices, breaking waves, and so on. Okay, but you also have turbulence in here. So in a deep ocean where the wind is slowly blowing over the surface, you will have lots of little wiggles which will interact through nonlinear interaction. So no breaking, no large-scale vortices, only weak amplitude waves, but still turbulent because the Reynolds number is large, and you have a dominant nonlinear terms. So very schematically, how do you write this in theory? So if you take Navier-Stokes equation in a world with waves, so for instance, with gravity to have surface waves here, and you imagine that you have something sustaining one wave with one given frequency, then through the nonlinear term, if you only consider this frequency, you will produce twice this frequency, so all the harmonics, but you might also produce some mean flow. So I won't be talking about mean flow today, but that's something that is also driven by libration. Now, if you introduce a second wave, so this nonlinear term between the first one and the second one might give energy to a third one. So you might start building resonant triadic waves interaction through this nonlinear term here. And this is very schematically the basics of wave turbulence, weak wave turbulence. So it's wave turbulence because the frequency and the wave number will spread over a large range only through this nonlinear interaction between waves. It's weak turbulence because the amplitude will remain small. We don't want our waves to break. And okay, so sometimes it will be between 3 waves, but sometimes 3 waves are non-resonant, and so you need to go to higher numbers of interactions, so 4 waves and so on. Okay? So this is weak wave turbulence. And so it's first a very nice playground for mathematicians because you have a small parameter now. The nonlinear interactions are small, which means that theoreticians can do something for us. But it also exists in a large variety of systems. So for instance, in vibrating plates, in optics, in cosmology with gravitational waves, and it's also directly relevant for us in geo and astrophysics. So I'm just showing here 2 examples. So with surface waves again, so this is what I was describing before, those slowly blowing wind on a deep ocean. So you see all that. The surface here is made by resonant interaction. So the number of waves which are involved in this resonant interaction depends on whether you are at small wavelengths. So capillary waves that are resonant by 3, while pure gravity waves are resonant by 4. But this is, anyway, wave turbulence at the surface of the ocean. Another example is with internal gravity waves, and I'm showing here a nice experimental study by the group in Lyon. So you have a wave maker in here, a stably stratified salty layer here, with, you see the very specific shape of the container. So you're introducing internal gravity waves by this wave maker at a given frequency. For internal gravity waves, one frequency means one direction of propagation. So you see you're making waves, and because of the specific shape of the container, the waves are looped in here. So that is a nice way to focus the energy of the wave along a trajectory. And if you slightly increase your system, the amplitude of your wave maker, this is what you see. So you don't have overturning, you don't have breaking, you only have still linear waves. But now you see that they don't propagate only in one direction, they propagate in various directions, meaning that you have a range of frequencies that are excited. We have also played with this numerically. So this is a spectrum so we just make a tidal forcing in a triply periodic domain, which is stably stratified again. So we make a tidal forcing with one given frequency, which is here at 1. The Brun-Weissala frequency, so the stratification, the buoyancy frequency is at 4. And starting from one frequency forcing, we end up with this whole spectrum with a -2 slope, which might be part of the explanation for the Garrett and Monk spectrum. Okay? So, if all that is clear, now let's go back to the main study of this workshop, so rotation. So for me, really, this paper by Yarom and Sharon in 2014 was really seminal in all this work. So they made a very nice experiment, a large experiment, which is about 1 meter in diameter and in height, rotating very rapidly, 120 rotations per minute, meaning that the Ekman is about 10 to the -6. And they introduced turbulence into their system using a jacuzzi at the bottom. So a lot of small jets coming in and coming out and coming in and coming out. So no specific pattern of injection, just random waves everywhere with a typical Rossby number of 0.006. And what is very specific in this experiment is that they introduce a nice measurements method, so a PIV capable of measuring the 2D field, but the 3 components of the 2D field. So how do they do that? You have a laser sheet here, the camera on the top. So that is classical PIV, so you measure the horizontal velocity in this plane, except that then they use a system to rapidly scan vertically. So that they have the horizontal velocity field depending on x, y, and z. Okay? The first result they showed is this type of spectrum, so the wave number, and the kinetic energy in this horizontal field.
Maybe dumb question, isn't that 3D 2C?
Yeah.
No, maybe.
Yeah, it's U8. It's irrelevant, but it's 3D 2C.
You're right. So it's a 3-dimension, x, y, z, and 2 components. Sorry for that. Yeah, you're right. So their spectrum here, the different colors show you the evolution as a function of time of the spectrum. This is the injection wave number, and you see that progressively the spectrum increase until it reaches a typical slope of -5.3. So it's a very nice measurement of the inverse cascade in rapidly rotating turbulence. That is something that is already known. Okay, so yeah?
In the previous case, do you know typical times between the different curves?
It's in tenths of seconds from what I remember. Okay, so this inverse cascade is well explained in 2D. In 2D, you have 2 invariants, the classical energy, but also the entropy. And so when you inject at a given scale, the only way to reconcile these 2 invariants is to have a direct cascade of entropy and an inverse cascade of energy. And the inverse cascade of energy, of course, has the same exponent as Kolmogorov, -5/3. Okay, so this is well known in 2D. When we are in geophysics, there is 2 ways of being quasi-2D, is to have a thin layer or to rapidly rotate, because if you rapidly rotate, you have invariance, large invariance along the axis of rotation following the Taylor-Klodman theorem. And just as an illustration, here is a numerical simulation from Benjamin. So it's decaying turbulence in rapidly rotating turbulence. You start by a random 3D pattern, and you end up forming these elongated columns. Okay, so that is what we have seen also several times using a convective forcing. Okay, so that was already nice to measure that in the lab. It's not easy. What they did also is to look at what is happening at higher wave number. And at higher wave number, they found a very specific way to plot their spectrum. Since they are measuring the horizontal velocity as a function of x, y, and z and time, so you can make the Fourier transform in all directions, but instead of plotting the spectrum in the classical way as a function of kx, ky, kz, and the frequency, they choose to plot it as a function of the wave number, the norm of the wave number, and the angle the wave number makes with the vertical axis and the frequency. And when you do that, so if you integrate over all wave number, so this is the angle the wave number makes with the vertical axis. This is a frequency. You see that all the energy, which is in color scale here, is aligned along specific curves. And these curves are actually exactly the inertial wave of my system. So inertial waves in a rapidly rotating fluid. I'm not looking at any density variation here. It's an isodensity fluid because of the Coriolis force. If you neglect the nonlinear term, the diffusion, you take twice the curl and so on, you end up with the classical Poincaré equation. And this is the dispersion relation of the inertial waves, which are solution of this Poincaré equation, where you see that the frequency depends on the rotation rate and only the cosine of the angle that the wave vector makes with the axis of rotation. Okay, so these waves exist in labs. So this is a nice lab experiment by the group of Hors. So they put a wave maker in a rapidly rotating system, and this is a PIV measurements of the waves they excite depending on the frequency they chose. Okay, so omega equal 2 plus or minus 2 rotation rate times the cosine of the angle. Okay, this is exactly these two curves here. So in these graphs, they just, on each line here, they put the maximum of the intensity of the energy spectrum. You see that all the maximum align along the dispersion relation for inertial waves. And you also have a lot of energy here, which correspond to the geostrophic component. Okay, so in rapidly rotating turbulence, you have actually two components. You have the one we all know a lot about, so the strong geostrophic turbulence, but you also have a bunch of inertial waves that travel all around here. And the question is, well, how does this coexist, compete, or couple? And this depends on the strength and the shape of the forcing you use. If you use a very strong forcing, or if you put energy into the geostrophic component of your system, almost everything will be sucked into this geostrophic component. Yet, this geostrophic component, this very turbulent geostrophic component, will still radiate inertial waves, And then the initial waves that are randomly excited like that, they might then nonlinearly interact to fill in the spectrum along the dispersion relation of inertial wave. So that is for strong forcing, or if you force directly on the geostrophic mode. But what happens now if you only force on waves? Then we might end up with a completely different state. If you force not too strong on waves, you might end up with having waves only in your system. So it means that, yeah.
Could you just give us an example of how you force directly the geostrophic modes? What do you mean by that?
If you take a paddle and you do that in rotating frame, you will have a column immediately, and then you can do whatever you want. Everything will go into this. Okay, so if you force strongly with a big plunger like that, you will also end up having, we will see that after. But if you force weakly on wave only, then following the mechanism, the triadic resonance as shown you before, we might end up having only inertial wave in the system, so a completely different shape of turbulence in rapidly rotating systems. So does it work? So to do that with Thomas Lerin, we did some numerical simulation, and to reach the lowest Ekman and Rossby number possible, we used the simplest configuration for numerical simulation, so a triply periodic box, rotating along the z-axis. The Rossby number here, it's a measure of the forcing, so it's an upper bound of the real Rossby number. In this case, we use a tidal forcing again. So we mimic in the bulk a tidal forcing, a periodic tidal forcing with one single frequency. Initially, we only have one single frequency. So at the beginning, we only see waves with one given angle. But this rapidly evolves towards this and towards this. So again, the geostrophic flow. This is for a Rossby number of 5 × 10⁻², Ekman 10⁻⁵. And then if we slightly decrease those two numbers, this is what we see. So in the very small dissipation, small forcing limit.
Actually, what's omega minus 0.5 mean? Is that different from X?
That's the frequency of the tidal forcing.
Oh, that's the forcing omega.
The frequency of the forcing.
Yeah, good.
And that's acting on large scales?
Sorry?
The forcing?
Forcing is large scale here. It's a tidal forcing over the whole box. And you see, and then you persist like that. So again, it's rapidly rotating, but it's completely different from what we are used to. If I come back to this nice spectrum representation with the angle of the wave vector and the frequency, and the color scale is the energy, you see that for my second case, all the energy again goes along the dispersion relation, of course. Why in the first case I have energy almost everywhere, and the main energy is actually right here where the geostrophic modes are. Another important point also for this case, so the wave case, if I look at the frequency, I see that I have a strong cutoff here at 2, which is because those are inertial waves, so they have a frequency which only goes between -2 and 2 times the rotation rate. So we have energy only below twice the rotation frequency and along the dispersion relation. So you have a turbulence only made by weakly interacting inertial waves.
Okay. Sorry, what was small enough? Like, what defines small enough?
That's the whole problem then. I will come back to that. That will be the rest of my talk. Just before that, so I showed you this case with what we call a linear forcing is actually a tidal forcing at one given frequency here, omega. So we force one frequency, but we don't select the wave number. For a given frequency, we can have a large range of wave number, but we end up with energy only here and this type of flow. We also tried another forcing, so a random forcing, so noise, delta correlated in time, choosing the wave number, the norm of the wave vector in a thin spherical shell. So in that case, we force only one scale, if you want, but lots of different frequencies. And if we force weak enough, again, we have only energy along the dispersion relation. Okay, so we have energy only along the dispersion relation, but it doesn't mean that we do really have, it's not a real proof that we do really have wave turbulence in the sense of only waves because they are nonlinearly interacting through triads. So to check that, what we need to look at is the spectrum. But the spectrum in that case, in case of wave turbulence, is very anisotropic. So you can not look directly at the spectrum as a function of k. You actually need to separate the perpendicular component of the wave vector, so perpendicular to the axis of rotation, and parallel to the axis of rotation. Okay? So I will give you a very hand-wavy demonstration of the Zakharov spectrum of inertial wave turbulence here. If you are interested in a much more rigorous demonstration, you're welcome to go and try to read Galtier's book. So very hand-wavy again. Huh? So you start by looking at the velocity at a given scale, square. So it's the energy spectrum which I'm looking at times the k perp, k parallel. And I just remind you here that the frequency, the inertial waves dispersion relation gives you the frequency as a function of the rotation rate, k parallel divided by k. K being square root of k perp square plus k parallel square. So then the trick here is that we have 3 different times in the system. The first one, which I will assume is fast, is the typical time scale of the wave, so 1 over the frequency. Then you have a typical time scale for nonlinear, nonlinearity. So the typical scale for nonlinearity, as usual, is the typical scale divided by the typical velocity, so 1 over k ul. And the third time scale here, it's the time scale for transfer of energy. And you remember in inertial wave turbulence, in that case, with 3 waves resonance, the transfer takes place through wave-wave interaction. So the hypothesis here is that the typical timescale for wave-wave interaction is a second order compared to the nonlinear term when non-dimensionalized by the typical fast timescale of the waves. So it means that my transfer typical timescale goes like the nonlinear term squared divided by the frequency, by the wave period, sorry. And then, as usual, if I just write down the conservation of the rate of dissipation through scales, so it's the velocity squared divided by the transfer time, I end up with this typical formula, which I can reverse to give you the spectrum, so the Zakharov-Kolmogorov spectrum, where you see that the energy depends on k perp to the minus 5.2, k parallel to the minus 1/2. Can we test that in the lab, in the numerical simulation? So, of course, the answer is yes. So those are the results for both the random forcing and the tidal forcing I showed you before. And you see, so it's not perfect, but it's already simulation at 10 to the for a Reynolds number 10 to the minus 7.5. That was the best we could do. Ekman number 10 to the minus 7.5, sorry. And you see that, well, it looks like, for sure, we have an anisotrope spectrum, and the slopes are not so bad. One key point here is that if you actually consider this spectrum in an isotropic way, so you forget that you have two different wave numbers in the two directions, you just mix them together, then you end up with a -2 isotropic spectrum. And you remember that the classical 2D spectrum for the direct cascade of entropy is k minus 3. So when you do measurements in a rapidly rotating case, it's not so easy to distinguish between what corresponds to that and what corresponds to that. So a direct cascade of entropy or the signature of wave turbulence if you do not separate the vertical and the horizontal components. And so those are our results, and you see, so the -3 is here, the -2 is here. It's clear for the geostrophic component of our numerical simulation that it is a -3.
Is that just a depth average or axial average? The geostrophic component?
Yes, it's a kz equals 0 component. But for the random forcing and the linear forcing of everything else, you see it's not, it's in between. So it's not very easy to figure out if you do have this type of turbulence in your system or not, only looking at the isotropic spectrum. Okay, so we think we have seen two different regimes of turbulence here, depending on the Rossby and Ekman number, but I must admit at this point that there was a trick in our numerical simulation. Actually, to be capable of showing this inertial wave turbulence regime, we had to add a tiny trick, so a small damping on the geostrophic component. And so we need to go to small Rossby, small Ekman, but even so, at the limit of what we are capable of doing with numerical simulation, we still need this tiny damping on the geostrophic component. And in this simulation, what I have done is, no, not me, Thomas Lerin has done, is that he has kept this damping at the beginning of the simulation, and then he has stopped it after a few times. And then this is the kinetic energy, the total kinetic energy, and the kinetic energy in the geostrophic component. So when we do that, initially the geostrophic component is very low, but even so, once we stop it, we reach a saturation state here. If we don't put at all this damping term for the exact same parameters, this is what we get. So almost all the energy is into the geostrophic component. So this is interesting, maybe because it means that we might have, in rotating turbulence, a bistability, two possible states and two completely different states of turbulence. Okay? So of course, in a real system, we won't have the specific damping of the geostrophic term. So what is our guess is that even if we are at a 10 to minus 7.5 Ekman number, we might still not be in the limit where we can have this inertial wave turbulence without the specific damping. But maybe at lower Ekman, lower Rossby, this will appear. This is the first explanation. The second one is that, well, maybe this specific damping is realistic, actually, because if you look inside a planetary core, geostrophic motion will extend all along the way until they reach the core mantle boundary. The core mantle boundary and the inner core boundary, for instance, or the ice sheet and the mantle in other cases. So they will actually be more damped specifically than all the other waves. But that's where we are today. Okay, so can we do that in the lab now? So in the lab, there has been 2 papers from the Hors group with Pierre-Philippe Cortet. So this is a very nice experiment. So maybe you all know that to excite internal waves or inertial waves, a usual wave maker is just a cylinder that you oscillate with a given frequency in your system. So the idea of Pierre-Philippe was to put several of them all around a circle like that. So they all oscillate with the same frequency, not the same phase, but the same frequency, such that in the center of your sphere, you have convergence of all the waves. So you might slightly increase, by focusing, you might slightly increase the amplitude. Okay? So here is the movie from his experiment. So this is all the cylinder out of phase, the large rotating table, and the PIV measurements. And then, again, there is one trick, following the trick we used before in our numerical simulation, is that he put honeycomb grid at the top and the bottom here to specifically more efficiently damp the geostrophic mode. Okay, and so here are some of their results. So what you see here is the kinetic energy in the wave as a function of the Reynolds number. So they are not coming from geophysics, so they use Reynolds number, but and not Ekman, but just Reynolds is Rossby over Ekman. Okay, so
does honeycomb mean something here? Why not just a flat plate?
Yeah.
Why wouldn't any flat plate work?
It will damp too much. Everything the same. Why the honeycomb specifically damp the things that are going into it. And the second trick they use is that their honeycomb is not exactly parallel. They are slightly with a slight angle so that they don't make modes. So they only have waves. It's a very smart trick. And the best answer is that it works. Okay, okay, so Reynolds number, kinetic energy in the waves and kinetic energy in the geostrophic modes. And then the black triangles are without those honeycomb and the red one with honeycomb. So what you see here is that at a given, with their system, starting at a given Reynolds number, they start having lots of energy. And if you only focus on the black triangles for now, you see that the start of the growing of the energy in the geostrophic mode is slightly after the one for waves only. So their claim is that between those two numbers, which are very close, in the absence of honeycomb grid, you have wave turbulence, and then you have geostrophic turbulence. And if you add the honeycomb grid, then you follow here almost the same train, except that you completely kill all the geostrophic mode. And so in that case, you have wave turbulence only. Okay, so it's not easy, but they do exist in idealized lab experiments. Another nice way to show it is that they plot the spectrum, so they don't have access to the three-dimension two-component PIVs. They just make a regular PIV, but what they can plot here is the ratio between the energy spectrum in the vertical direction and the energy spectrum in the x direction. And they assume isotropy in the xy in the horizontal plane. And in that case, for inertial waves, we have an exact solution of the ratio of the two spectrum. And those are the measurements. And what you see, it's perfectly aligned with the theoretical prediction for inertial waves only, down to very low frequency, where, of course, you recover some geostrophic component. So they have made inertial wave turbulence in the lab. Okay, so now what we have seen that it is possible with some trick or by going to very low Ekman number, low Rossby number, it's possible to excite inertial wave only, but in most cases, there is a net tendency of what we can do in lab on numerics to produce a geostrophic flow. This actually is kind of a theoretical paradox because there is a famous Greenspan theorem from '69 that says that if you have triadic interaction only, then there is no resonant triadic interaction capable of transferring energy into the geostrophic mode. So this is problematic because most of the case we do see that, and it's just opposite to the theory. So how, why, and where does the threshold in Rossby number John was asking come from? So there are two theories, one by us and the other one by the group of Pierre-Philippe. So the Greenspan theorem is really for triadic resonance in the limit of 0 Ekman number, 0 Rossby number. So our model is just to say that, well, let's look not only at exact resonance, but at near resonance triadic interaction. And in that case, if you allow for triadic resonance of order k Rossby square, then you might find triadic resonance involving one geostrophic mode. This is our theory. The second theory is instead of doing triadic resonance, you do 4-wave resonance. And then you might find resonant 4 waves interaction involving one geostrophic component. And just for the story, there is one theoretician involved in those two competing models. And I'll let you know who it is. He's in this room, maybe over there. So he's competing with himself. So we don't know which model is good. Maybe both are good, actually. They are not opposite. They could coexist together. The point is that they both predict a threshold. Rossby goes like Ekman 1/4. And that will be important for the geophysical applications that I will now look at. Yeah, it's less than 1/2. Yeah. So can any of these apply to planetary cores on subsurface oceans? Of course, if it does, it's very important because it changes everything we know about energy dissipation, mixing, magnetic properties, so including induction and dynamo, everything has to be re-evaluated, okay? And so the first question is to know how can we excite inertial waves, those waves, into planetary fluid layers, being cores or subsurface oceans. Okay, so this is what we all know. The first way to drive intense motion in rapidly rotating cores or subsurface ocean, we have seen that this week, is through buoyancy-driven flow, and buoyancy-driven flow mostly aligned with the axis of rotation. And buoyancy-driven flow works perfectly well for lots of things, including the magnetic field of the magnetic field of the Earth, for instance, with those reversals and so on. It works perfectly well for the Earth today. The point is that the energy budget, for instance, to drive the Earth's dynamo is very tight. And so this model of convection of a dynamo might not work for smaller planets, which cool down more rapidly. They might not work for stably stratified ocean, and I have asked several times this week whether or not the ocean the subsurface ocean were stratified, so I guess we don't know yet. So the point is that maybe it's not buoyancy driving flow which are driving all the flow in cores and subsurface ocean. So if it's not the heat escaping the planet, then you need another type of energy, another source of energy. And actually there is one very obvious, that all planets and stars, everything is rotating. And rotation is a huge reservoir, so the spin and the orbit of all planets is a huge reservoir of energy, huge. Just to give you a number, an example, if you look on Earth, the rotational energy, including the spin and the orbit around the sun, gives you this number. So we cannot say more about that, but if we need to sustain the magnetic power we need to sustain the dynamo today, it means that you can extend you can sustain the Earth dynamo during 3 to 63 gigayears. So all I want to say here is that we have a huge reservoir of energy. The problem is that this huge reservoir of energy is useless if you have planetary fluid layer, no matter what the shape are, which are rotating in solid body rotation. If you have planets rotating in solid body rotation, the fluid follows the solid body rotation and nothing happens. So we need a way to convey the energy into the system. And lucky enough, the planets are not rigid body rotating at a constant rotation rate, but you have things like libration, which correspond to small perturbation of the rotation rate of the planet. You have precession, which correspond to small change in the direction of rotation of the planet as a function of time. And you have tides, which correspond to small change in the bulge in the shape of the planet as a function of time. All those perturbations are, of course, tiny, but they are very regular, so they can force waves. Okay, so typical order of magnitude. So this is a change in the libration rotation rate as a function of the mean one is 7 × 10⁻⁵. The precession of the Earth compared to the rotation rate is 10⁻⁷. The amplitude of the bulge plus or minus 30 centimeters compared to the size of the Earth is 10⁻⁷. So very, very tiny, but very regular. So that we can study in the lab. And I show you here, so it has been a long work, both here at Spin Lab and also in my lab at IRC, and I show you example of different setups. So this setup is for libration by Granan. So you see you have a tank here, which is oscillating on a rotating table. Here it's precession, so you see you have a tank, a spheroidal tank here, rotating along an axis, which is inclined, and this axis is also rotating as a function of time. And this is a tide experiment. So the tide experiment, it's a spherical container, but I have two cylinders on the sides that come and compress the shape. Okay, so I distort my sphere to an ellipsoid, and I have a different motor for rotating the deformation, so the tidal distortion, and the rotation rate of the planet. And here you just have visualization of what happens when we choose the right frequency of excitation, of perturbation into the system. So you see, you start exciting waves, and then it grows in amplitude, and it degenerates into some turbulent flow. Okay, so how can we, from this perturbation, how can we inject energy into the fluid? So the first method is through direct bulk injection by parametric resonance instability. So we have worked a lot on this, but actually the pioneer work was by Wilhelm Malthus in the 60s, and then it was completely forgotten by the planetary community during 40 years or so, and then we restarted from that in the 2000 and so with John and Jérôme Noir, and essentially. So what is the idea here is that from tides, libration of precession, I have some kind of base flow. So it's mostly rotation plus some tiny perturbation. And this is tiny but regular, so it means it can excite a parametric resonance. And the mechanism is just that this tiny perturbation from the base flow excite a parametric resonance with two inertial waves. So we can do all the calculation for all the different cases here. We can find the linear threshold of instability and so on. This is well known. I will not talk about this here. So we have a threshold that goes like the Rossby number of the perturbation must be larger than the square root of the Ekman number. The square root of the Ekman number is just the viscous dissipation at the boundaries, and the Rossby number is just the amplitude of the forcing. As soon as the Rossby number is large enough, you excite this type of triabolic resonance. So of course, the prefactor here depends on the excitation you're looking at, but it's always the same type of order of magnitude. And so we can extrapolate from the lab around 10⁻⁶ to 10⁻⁴ in Ekman number to the planet. And you see that this comes from a work by Daphne. We have a bunch of planets that are actually in the unstable domain. Other things that we have done also is that to show that these flows are dynamo capable. But all the question is, this was before everything I showed you in the first part of my talk. And actually what we have seen is that we know, so we explained theoretically well the linear part of the destabilization, and then this grows in amplitude, and what we have studied is the 2D geostrophic turbulent saturation of this flow excited by libration, precession, or tides. Okay, and this is actually very similar to usual rotating convection. It's mostly geostrophic. So maybe it's not such a surprise that we recover a dynamo and so on. Actually, it's just the source of the excitation is different, but the shape of the flow is very similar. Now, are we sure that we are in this case, or could we be in this 3D wave turbulence? Because again, I start from the base flow, which excites 2 waves, and then each wave can resonate triadically with 2 other ones, and so on, and so on. So I do not put any energy in the geostrophic component with my forcing, so I might as well be in this saturation state. And then everything has to be re-evaluated. Okay, the problem is that it's very tricky to reach that with this realistic type of forcing because, as I've shown you before in the idealized triply periodic simulation, we need to go to very small Ekman, very small Rossby. We had not that problem for the linear destabilization process because, as usual in the lab or in the numerics, we can compensate the fact that we are at larger Ekman number by forcing more. Here, we cannot do that. We really need to force slowly to reach a good regime. And so that's why we have built this new setup, a little larger than what we have done before, actually 3 times larger and rotating faster. So it's an ellipsoidal container. So it's the same as the experiment by Granham we did at UCLA before. It's an ellipsoidal container, which is on a motor that oscillates as a function of time, and the whole setup is on the rotating plane. Shut down, yeah. This is Thomas, by the way, and this is Sandeep. Okay, so does it work? So I need to hurry. So this is just 2 spectrum I show you as a function of the frequency. I just changed the forcing by 30%. So here, everything is at Ekman. I forgot to tell you 5 × 10⁻⁶, so 1 order of magnitude smaller than what we were doing before. And this is for a Rossby of 5 × 10⁻², and this is for 7 × 10⁻². And actually here we have 2 completely different behavior. Here we have lots of peaks between 0 and 2, while here we have mostly the first, so the forcing peak, the first resonance, and then something at 0 frequency. It's more clear maybe if we look at the mean zonal flow. So we make an horizontal PIV plane, and we look at the mean flow in the azimuth. And you see here that slowly increasing the Rossby number, we go from a flow with almost no zonal flow, so only waves, to suddenly, it's really a threshold, a big giant vortex in the middle of our container. If I focus on this case, I can decompose the different peaks, and actually I can show the different wave-wave-wave interaction when I filter out each of these peaks, and from the PIV measurement, reconstruct the shape of each coupled mode. Okay, so this is, again, Rossby Ekman. This is a threshold for the libration-driven instability, and those are the experiments. And from the experiments, what we might expect is a threshold that goes like a Rossby Ekman 1/2. You remember maybe that before I talked to you about a Rossby Ekman 1/4. So we don't know exactly what is happening. Our theory shows that there should be a transition between 1/4 and 1/2 at moderate forcing. But it's still not completely clear. What is clear is that if you extrapolate from what we do in the lab towards planets, the planets are actually very close to the threshold of the elliptical instability. So it means that if we extrapolate the experimental threshold, it's here. If we take the theory, it will be a 1/4, so it will go away from this first threshold here. In any case, the planet, if they are unstable, are, by these instabilities, are in the inertial wave turbulence regime, not in the geostrophic one. So in any case, wave turbulence may dominate in planetary cores, of course, which are not convecting. Okay, so bulk injection of waves with this resonant instability is one way to put waves into the system. There are other ways. One possible could be the flow over topography, and I'm mentioning here a work by Jérôme Noir, who has played with Lego to make a rough bottom in a spin-up experiment, and he has shown that when he was just slightly changing the velocity of his rotating container, he was emitting a lot of waves. So the flow through the roughness, and that's also something that is well known for the ocean. Dan showed a picture of that before. A flow through some roughness will emit waves in the system. And of course, core mantle boundary, inner core, ice sheets, all that may be rough. So that's the first, that's the first example. The second example might be boundary turbulence. So if I come back to my libration forcing, so libration forcing is in the rotating frame is just doing that. So during part of the cycle, I'm centrifugally unstable, while part of the circle, I'm centrifugally stable. So even if I don't destabilize the bulk of my system, the boundary layer will be accelerated, decelerated, accelerated, decelerated. So it will turn out that the boundary layer will become turbulent when its local Reynolds number will be larger than 100. So this is a paper by Jérôme again with this experiment at UCLA. So you see here, he has saturated his container with some flakes that reflect the light. And so what we visualize here is the flow, the shear flow within the boundary layer. And you see that, so the green here corresponds to that case. You have long vortices within the Ekman layer here, and then it becomes fully turbulent. So that only takes place in the boundary layer, but then we have done some numerical simulations that showing that if the boundary layer becomes turbulent, then it will radiate waves in the interior. So those, it was a long time ago already. It's only axisymmetric, and now we are working with Ankit to make the same thing, but in fully 3D, and to study the turbulence in the interior. It will be much more interesting. Last, so Dan has shown that before, we can also think that part of the ocean or part of the core will be convective. So we will have convection in here, but then this can excite waves in the non-convective part. So again, interesting thing might happen here. Induction, specific dissipation, and so on. So I'm completely cheating here because in this paper, it's non-rotating. It's actually stably stratified, so it's the same kind of thing that Daniel showed us before. But stratification or internal gravity waves or internal inertial waves, they are really the same. So everything that I've said to you today would work in a non-stratified domain or in a stratified domain. It will work about the same. So so as a conclusion, I hope I have convinced you that in rapidly rotating turbulence, we might have actually two very different regimes. The strong turbulence that looks like that, the weak turbulence that looks like that. If we have planets or systems that are like that, we don't know almost anything about it, so we have to study induction processes, magneto-hydrodynamics, dynamos, dissipation, anything. Anything has to be reevaluated. So this we know perfectly well that it makes a dynamo. For the inertial wave turbulence, actually, there has been one work on that by Moffat in the 70s. And he has shown that through a classical, at that time, mean field alpha approach, that if you take a packet of waves and you break the helicity symmetry, you might end up with a large-scale magnetic field. So you have a real decoupling between the small-scale waves that produce an alpha effect, and you have an alpha square dynamo that appears with a magnetic field that appears at large scale. Okay, but that was with the mean field alpha theory only, and it was also, you need to find a realistic way to break the helicity in the wave packet you emit, which is not easy in geophysics. So right now we are working with Daniel and Emma Kaufman to look at this alpha theory, but using not the alpha mean field approach, but the real induction equation from the waves. And for now we have used only two, we have put an excitation with only two waves. And for now, you see that the theory from Moffat so this is a growth rate of the magnetic field. the theory of Moffat, the mean field theory, crosses the line of 0, but the calculation from EMA, the tangent is 0. So maybe 2 waves is not enough. We need to put some more, but it becomes more difficult, theoretically speaking. And yeah, and just to finish with, we have heard a lot about subsurface ocean here, but if we are really in that case in some stably stratified subsurface ocean, well, we don't know anything about dissipation, heat and chemical transport, and magnetic induction. And I stop there. Thank you.